So welcome to the next unit in the topic of structure and bonding. By the end of the unit, you should know about intermolecular forces, the relative strength of these intermolecular forces, and be able to deduce the type of intermolecular forces present in a substance, and explain the physical properties of that substance based on the intermolecular forces. So we will first look at intermolecular forces, or IMF, which will be the shorthand we'll use from now on. So intermolecular forces are the attraction between molecules that have temporary dipoles, permanent dipoles, or hydrogen bonding. There is a special type of intermolecular force known as the van der Waals force, but these only include one or two intermolecular interactions between molecules. So the three main types of intermolecular forces are London dispersion forces, which are the interactions between non-polar molecules from temporary dipoles. So basically, it's the dipoles induced by the interaction of these molecules together. We then have dipole-dipole forces, which are from permanent dipoles of polar molecules, and a special kind of dipole-dipole force known as hydrogen bonding, which involves the bonds with hydrogen, with molecules involving hydrogen, which are directly bonded to nitrogen, oxygen, or fluorine, and only those atoms. So the first intermolecular bond we're going to look at are the London forces. They are the weakest of the three intermolecular forces, and they're also called dispersion forces. And we'll look at an animation involving them in the next slide. And they're caused by the motion of electrons around a nucleus. Okay, so you can see here that we have an unsymmetrical distribution of charge between the negative electrons and the positive protons, which happen randomly. Okay. And this motion of electrons around the nucleus causes this unsymmetrical distribution. And because of this asymmetry, this leads to temporary dipoles, also called instantaneous induced dipoles. So the atom ends up with a positive pole and a negative pole. And what essentially happens is this forms a dipole in one molecule, which can then induce a dipole to form in an adjacent molecule nearby. Okay, so if this molecule is positive, then that's going to attract the electrons of an adjacent molecule and make it slightly negative and induce a dipole. So the first dispersion forces increase with atomic radii, and we'll explain later the reasons behind this. So the next part of the video will be a short animation illustrating dispersion forces. So the strength of these intermolecular forces, in terms of London forces, can be increased in three ways. A large radius contains more electrons. So in this particular example here, bromine would have larger London forces between bromine molecules. So the reason behind that being you get larger dipoles. So bromine should theoretically have a higher boiling point than chlorine, which has a smaller ionic radii. The size of the electron cloud also increases the London forces. Okay, so for example, with larger molecules, so if we compare the boiling point of propane to the boiling point of butane, we should see that butane's boiling point is higher because there are more interactions between the molecules. And because there's more interactions, there's more London dispersion forces. And finally, less branching should allow more surface area interaction. So pentane should have a higher boiling point than its isomer 2,2-dimethylpropane, because it's a nice kind of reasonably flat molecule compared to this branch molecule, which means that there's not much packing, and this reduces the amount of London forces between the molecules. And indeed we see that, 36 degrees compared to 9 degrees Celsius. So that was London dispersion forces. The next type of intermolecular bonding is dipole-dipole forces, and these occur in polar molecules because they create permanent dipoles. Okay, for example, like in water, okay, where the hydrogen is slightly positive and the oxygen is slightly negative. So the partially charged ends of the molecules attract and repel each other. However, you must also remember that London forces are still acting within these polar molecules, to a lesser extent due to the decreased strength, but they are still acting upon the molecules. So in terms of dipole-dipole forces, polar molecules, polar covalent molecules at least, have slightly charged ends. Okay, so we can see this here with acetone here. There's the slightly negative end of the oxygen and a slightly negative end, slightly positive end of the carbon. So adjacent molecules which are also polar will be attracted. Okay, so the slightly negative end of oxygen of the acetone will be attracted to the slightly positive end of the dipole of acetone in the adjacent molecule on the carbon. Okay, these opposites attract, and this larger electronegative difference causes, or the larger the electronegative difference, the more the attraction between the molecules, which we will now look at as a special example, that being hydrogen bonds. Okay, so hydrogen bonds are a special case of dipole-dipole interactions and intermolecular bonding. And a hydrogen bond is an attractive force that forms between an unshared electron pair and a hydrogen atom covalently bonded to a strongly electronegative element, in this case nitrogen, oxygen, or fluorine. Okay? Hydrogen is the only reactive element without an underlying layer of electrons. This makes the hydrogen bond about 5% stronger than an average covalent bond. So it's actually quite a strong intermolecular bond. Essentially, it's just a naked proton when it's bonded to a strongly electronegative element. So in terms of the hydrogen bonds, which are of course fluorine, oxygen, and nitrogen bonded to hydrogen, have a free lone pair. Due to the small size and high electronegativity of nonmetals, okay, the small size of the proton, for example, means it can get really close to and get adjacent molecules. So that the closer molecules are together, the stronger the bonds between them. This creates also a large charge difference between the hydrogen and the electronegative atom. Okay, so this is going to be very strongly negative, and this is going to be very strongly positive because of the high electronegativity, pulling electrons towards the electronegative atom. It's essentially basically a super strong dipole-dipole bond, which you can see here. Okay, so a covalent bond, by definition, is about 2.8 angstroms. Here we have the hydrogen bond being 1.8 angstroms, quite close. And we can see this in boiling point trends in terms of the differences between the bonding, intermolecular bonding. So in phase changes, so when a liquid becomes a gas or when a solid becomes a liquid, what's essentially happening is that electromagnetic forces are being overcome, especially in the transition between liquid and gas. So in answering questions, you need to be sure to explain using the words intermolecular forces and how they affect the bonds between particles. And London forces, remember, are always present. Okay, so what we're going to do now is just go through this graph and point out the reasoning behind each of the graphs. Okay, so water stands alone with the amount of energy it requires. Okay, a high boiling point means that it requires a lot of energy to break these intermolecular bonds. And you can see that water is kind of an anomaly. There's a large difference between the hydrogen sulfide and water. And the reason why is because you've got your H bonding. Okay, hydrogen bonding, very strong. A dipole-dipole bond, that explains the large difference. And as we go up, you can see that the atomic radii is increasing, okay, as we go down the group, and that explains the reason why the boiling points begin to increase again, because you've now got stronger and stronger London dispersion forces, larger atomic radii, larger dipoles. Okay, again with HF, let's rub that out there so we can get to HCl. Again, HF, hydrogen bonding, fluorine highly energy negative. So again, a big difference between the boiling points of hydrogen fluoride and hydrochloric acid. And again, as we go up this way, you can see as we move down the period from chlorine to bromine to iodine, you can see that the atomic radii is increasing. So again, London dispersion forces are also increasing. So now looking at the green dots, so again, ammonia, hydrogen bonding, nitrogen right next to hydrogen, and high boiling point at about -55. As we go across, you'll see that phosphine here has a lower boiling point, and the reason, of course, again, hydrogen bonding is no longer present, so that's a very strong bond that's no longer there. And we go from phosphine to arsenic to lead, Sb. You can see again the ionic radii is increasing, London dispersion forces are increasing. Okay, so the difference between phosphorus and antimony, essentially as we go down the group, is going to be increasing ionic radii, more London dispersion forces. And finally, we have these now covalent molecules. Okay. So we've got CH4, okay, methane, and then we have the silicon. So we're basically, again, going down the group, to carbon to silicon to germanium to tin. And again, as we go down, we're going to be increasing ionic radii, so there's larger London dispersion forces, larger dipoles as we go down the group, as we replace carbon with tin. So again, we're going to see an increase in boiling point due to this. So the general trends are illustrated here. With London forces are the weakest. They tend to, well, they involve non-polar molecules, so butane would be an example. Then we get to dipole-dipole interactions. They're slightly miscible in water. So, for example, propanone, or known as also as acetone, a higher boiling point than butane due to these dipole-dipole interactions, and can also now slightly dissolve in water. Hydrogen bonding, compounds with hydrogen bonding are miscible with water, and again, the boiling points are still increasing and increasing because it's a very strong bond. Then, going back to previous units, ionic bonding is a lot stronger than hydrogen bonding. And remember, it only conducts electricity when liquid or aqueous. So sodium chloride, for example, has a higher melting point than water by a lot. Then we move on to metallic bonding, which we'll look at in the next unit. Able to conduct electricity, not water soluble. And the melting point's regulated by the valence of the metal, the size of the metallic atom, and also the packing of these atoms. And finally, we have giant covalent, which has the highest melting point of the bonding that we've looked at. It's insoluble both in non-polar and polar solvents, and does not conduct electricity except for graphite, of course, due to its free electron. So examples of that are diamond and graphite. So this is a diagram further reinforcing that and comparing the energies. Okay, so for ionic bond, which is intramolecular, between ions, okay, looking at about 400 to 4,000 kilojoules to break those bonds, so quite a lot of energy. Covalent bonds, say for example between hydrogen atoms and the hydrogen molecule, again high energy, 1,100. Okay, we haven't really looked at giant covalent there, but that's going to be actually above, okay? So giant covalent will be above here. Metallic bonds, which we'll look at in the next unit, about 1,000 to 75 kilojoules per mole. So again, quite a lot of energy required. Okay, so now looking at those, so looking at about, say, 2,000 kilojoules to break those kind of bonds. Now looking at the intermolecular bonds, which are a lot weaker. Okay, so a hydrogen bond would be about 10 to 40 kilojoules. And then we're looking at dipole-dipole bonds, which are about 5 to 25. And then look at very weak individually. London dispersion forward is 0.05 to about 40 kilojoules per mole, depending on the particular atom or molecule you're looking at. So you can see, in terms of relative strength, that giant covalent are the strongest, and then London dispersion forces, being an intermolecular bond, are the weakest. So in terms of intramolecular bonding affecting the boiling point of substances, so we've already looked at that in the way in that graph, but when a liquid turns into a gas, the attractive forces between the particles are completely broken. So in a way, the boiling point is a good indication of the strength of the intermolecular forces between those molecules. So covalent macromolecular structures such as diamond have extremely high melting points and boiling points because essentially their intermolecular bonds are actually intramolecular, especially for like diamond and silicon dioxide. So they don't really have much intermolecular forces. It's mainly intramolecular forces, and that explains their high melting and boiling points. It requires massive amounts of energy to break those intramolecular bonds. Metals and ionic compounds tend to also have relatively high boiling points due to the very strong ionic electrostatic interactions between ions. Hydrogen bonds are the strongest of the intramolecular bonds, so they're in order of 1 to the 10th the strength of a covalent bond, whereas London forces are in the order of less than 1/100th of a covalent bond. And finally, the weaker the attractive forces, the more volatile the substance. So non-covalent molecules tend to be a lot more volatile than polar covalent molecules, especially those with hydrogen bonding. And so to finish off and look at in our summary of intermolecular forces, let's just compare compounds and see the strengths of the relative intermolecular forces acting on them. And the presence of hydrogen bond can be illustrated by comparing the boiling points of HF and HCl. Okay, so HF has a boiling point of around 20 degrees Celsius. When we compare hydrogen chloride, which doesn't have hydrogen bonding, the effect is quite dramatic. Okay, it's minus 85 degrees Celsius, which means that the intermolecular forces are a lot weaker in the hydrogen chlorine because less energy is required to break these intermolecular forces in order to initiate this phase change. And it can be illustrated again also by the comparison of the boiling points of water and hydrogen sulfide. So water, as we know, has a boiling point of 100 degrees Celsius. Hydrogen sulfide has a boiling point of 140 degrees less at 60 degrees Celsius. So again, amazing the effect of the water in terms of strength of bond in order to be broken in order to have that phase change occur. So comparing ammonia with phosphine, again the hydrogen bonding of ammonia. Okay, so nitrogen being less electronegative than fluorine, so you'd expect it to be a bit weaker in terms of hydrogen bonding, but still it's quite a powerful hydrogen bond all the same. Ammonia's boiling point is minus 33 degrees Celsius, whereas phosphine is minus 80 degrees Celsius. So you can clearly see there's still the effect of hydrogen bonding on the melting point of these two different species. Moving into the organic molecules, comparing propanone with ethanol, propanone has a boiling point of 56 degrees Celsius, whereas ethanol has a boiling point of 79 degrees Celsius. Showing again the effect, even though there is a dipole-dipole interaction between different molecules of propanone, the effect of the hydrogen bonding is to increase the boiling point of ethanol by around about 20 degrees Celsius. So again, it requires a lot more energy. And finally, looking at these three different examples here, we have propane, which is only London dispersion forces because it's non-polar covalent. We have ethanol, which has dipole-dipole interactions, and when we have the hydrogen bonding of ethanol. So propanone has a boiling point of minus 42 degrees Celsius. Ethanol has a boiling point of 20 degrees Celsius. And as we've just seen, ethanol has a boiling point of 79 degrees Celsius. So you can clearly see the massive difference that intermolecular forces have on the boiling points of different species.